Swayam Prabha. Digital India. Educated India.
Hello everyone. Welcome to another session of our NPTEL on Nonlinear and Adaptive Control. I'm Shrikant Sukumar from Systems and Control, IIT Bombay. In this week number 7, we are already underway into learning algorithms that are expected to drive systems such as what we see in our background and orbiting spacecraft around the Earth. So, what we were doing until this last time is to look at first the matched uncertainty case. That is when the parameter was in fact matched with the adaptive controller. And we actually learned how to use a backstepping based Lyapunov design to construct a control and an update law, and therefore an adaptive controller for such a system, right? And we also, of course, just this stability analysis, we also looked at a little bit of how to talk about persistence, right? So basically we did all that for the matched case, and then we moved on to the case of parameter unmatched with the control, right? And the first again looked at the known parameter case in order to understand how the backstepping design will work. So we got a fair idea of how the control would be. Yeah. So basically, we just started doing this, right? So for the known parameter case, we in fact first looked at the model, right, where we have the parameter now in the first state instead of the second where the control appears, right? And the aim is the same, which is basically to drive x1 and x2 to 0, right? So again, slightly different because we're not looking at the tracking error problem, but as I said last time itself, this is exactly the same. Yeah, even if I was considering a tracking error problem, the methods that we're using would apply almost identically, right? So great. So in order to ensure x1 to go to 0, we designed a controller, yeah, assuming that x2 is the control for the x1 state. This is again standard in the backstepping based method. And since the parameter is known, I can apply this kind of a control to get this nice ideal system. And we also choose this nice V1, right? Now, because we know that x2 is not identically equal to x2 desired, we try to do the next best thing, that is drive x2 to x2 desired. And this is where we get the motivation for choosing the second piece of our Lyapunov function or Lyapunov candidate function, and that is the error between x2 and x2 desired and a quadratic constructed out of it. All right. And now we know very well that v2 dot turns out to be of this structure, right? And if we choose u to be x2 desired dot minus k to x2 minus x2 desired, right? So then I know that this gets cancelled out and I get a nice negative term. So I get basically v2 dot as minus k2 x2 minus x2 desired whole square. All right. So this is where we were, and we're going to start from here. So I'm going to mark our lecture as lecture 7.3, starting this point. All right. So as always, just like before we did in backstepping, we just add up the two pieces to get a candidate Lyapunov function for the consolidated x1 x2 system. All right. And we actually start taking the derivatives carefully, right? So the x1 v1 was just x1 squared by 2, so v1 dot is x1 dot, and v2 dot, by virtue of this analysis, yeah, is just minus k2 x2 minus x2 desired squared. All right, great. Now we plug in for x1 dot, of course. Yeah, so what does it turn out to be? X1 dot is x2 plus theta f x1, so I get x1 x2 plus x1 theta f x1. Yeah, And now we also know that, of course, we want to write x2 in terms of this variable, right? And that's what we do, right? So that's what we do. So what is this? So basically, I have, we just write, let me look at this carefully, if this is done correctly or not. All right. So if we go back and look, in fact, I'm going to reproduce the expression right here. So x2 desired was defined to be minus k1 x1, right? Plus, well, I believe minus theta fx1, right? Okay. So in fact, the way this manipulation is done, it's fine. That's okay. So what we do is, if I actually don't write x2 as this, but I simply replace theta fx1 from here. Yeah, so if I do that, theta fx1 is actually equal to minus k1 x1 plus x2 design. So this will actually be a plus sign, right? This will actually be a plus sign. Let's see if I got this correct. So just a second, let me go back and check. Right, so x2 desired is minus k1 x1 minus theta fx1. All right, and if I go here, which is what I wrote here, x2 desired is minus k1 x1 minus theta times fx1. So if I replace for theta times fx1 from here, I get minus k1 x1. Yeah, I made a mistake. This should be minus k1 x1 minus x2 desired. Yeah, this is what I was sort of looking for. And this is correct. Yeah, this is correct. Yeah, that's what I was wondering. All right. So now if you combine, so this term is of course nice. It's minus k1 x1 squared. And if I combine these two terms, yeah, I get x1 times x2 minus x2 desired. All right. All right. So essentially there is a step that's missing here. So I'm going to write it. So this is actually equal to minus k1 x1 squared minus k2 x2 minus x2 desired squared plus x1 times x2 minus x2 desired. All right, this is very similar to what we had in the previous backstepping also. Okay, this is very similar because you have nice two negative terms and then one mixed term. This is very standard in what happens in backstepping type analysis. Yeah, if you go back, I'm going to try to actually demonstrate that similarity, right? If you see, I had minus k1 e1 squared minus k2 psi2 squared, which is the backstepping error variable, and then I had a mixed term in the e1 and a backstepping error variable. So if you look at this, I have the exact same scenario here. I have one term in minus k1 x1 squared, another term in the backstepping error variable quadratic, and a third mixed term in the x1 and the backstepping error variable. All right, so this is exactly what you tend to get. And from this point, you know that I can do, I can simply do what is called sum of squares, which just involves using the inequality that this guy, I will write it once more, is less than equal to half x1 square plus half x2 minus x2 desired squared. All right, so once I use this inequality here, which is essentially the sum of squared process. Why is it called the sum of squared process? Because we are writing these mixed terms, a b type terms, in terms of squares, a square and b square, because those are the terms we have here. And so once you combine these, you get exactly this expression, which is again very similar to what you had even in the matched case. So with this backstepping type procedure, you are getting almost a rather similar a v dot as the matched case also. Yeah, so this is why backstepping is a rather universal you know um, method of control design that can be used in many different contexts. All right. So anyway, um, so with this, you know that if I choose k1 and k2 to be greater than half, then I have v dot negative definite. Then of course, which immediately helps me to apply this Lyapunov theorem, which immediately proves that x1 goes to 0 and x2 goes to x2 desired. So essentially you have, I mean, all round a global uniform asymptotic stability. I mean, you have all essentially the best property that you can look for. All right, so great. Yeah. So in fact, if you look at it very carefully, you can even conclude global exponential stability. Yeah, if you so desire. Yeah, you can even conclude global exponential stability because you can see that it is the same order and all that. But since we're dealing with nonlinear systems, mostly we don't really mention this because more often than not, this is not possible to achieve. Yeah. So anyway, so now what do we know? We have started off looking for x1 to go to 0 and x2 to also go to 0. So this always remains a question. Did the construction of the backstepping error variable actually mess with our tracking or the stabilization control objective? Yeah. In this case also the answer is no under certain assumptions. Okay. So what are those? So x1 goes to 0 is obvious, x2 goes to x2 desired, and x2 desired was this quantity, right? Now what do I know? I know that this is going to 0, right? So if x2 desired is going to 0, right? So if I want x2 desired to go to 0, because I want x2 to go to 0, so this will happen only if x2 desired is going to 0, right? So I want this to happen. Okay, and so we sort of make this sort of an assumption, right? I mean, you can think of it as an assumption, right? This is an assumption, yeah, because eventually, yeah, this is something beyond the system data, right? This is an assumption. And if we do have such an assumption that f at 0 state is 0, then you have that x2 goes to 0, and we are done. All right. Now, one might be tempted to argue about the reasonableness of this assumption. Okay. Now, why one would say that this assumption is in fact reasonable, well, at least reasonable, is that if you have, if you're looking for equilibrium, if you're looking for x1 and x2 equal to 0 to be the equilibrium of the system, right? So how do you find the equilibrium? Typically, you will assign the control to be 0, and you will try to find the right hand where the right hand sides are 0. So with the control 0, this is anyway 0. But if I want this guy to be 0, and I want x2 to also be 0, because I want x1, x2 equal to origin, that is 0, 0 to be the equilibrium of the system, then if this guy is 0, then this guy also has to be 0. And theta is some, of course, constant non-positive, constant non-zero unknown. Right? So constant and non-zero. If it's 0, then there is nothing to do here. Right? So if x2 is 0, or x2 equal to 0 is an equilibrium, and then this also has to be 0 at x1 equal to 0. And otherwise, x1 equal to 0 is not an equilibrium solution. Okay, if f0 is not equal to 0, yeah, so the point is that we're trying to make is, if f0 equal to not equal to 0, then x1 x2 0 0 not an equilibrium. Okay, so and remember that we're always trying to analyze stability of an equilibrium. It doesn't make any sense if we are trying to analyze the stability of a point which is not the equilibrium. So therefore, if we are interested in going to a point 0 0, then it better be an equilibrium of the system. And so f0 equal to 0 is a very reasonable assumption to ensure that x1 x2 equal to 0 0 is in fact an equilibrium of the system. All right. So this is a fairly reasonable assumption, no problem. Yeah. And so we've been able to prove for the known case with this kind of a control law, right? So now one of the question that also arises is, what does this control law look like? Because there is an x2d dot, right? So you essentially have to take a derivative here, right? So it's use this expression, take a derivative, right? So this is minus k1 x1 dot, which is minus k1 x2, and this is minus theta f dot, which is partial of f with respect to x1 dot. Oh, sorry, I should just say. So there is x1 in both. So this is like minus k1 minus theta partial of f with respect to x1 times x1 dot. All right. So this is essentially the control. And if you want to substitute this, you can of course substitute for this x1 dot as x2 plus theta fx1. Yeah, so this is a very implementable control. So this is minus, of course, k2 x2 minus x2 desired. Okay, so that's how it works then. So x1 dot is just this. Yeah, this is a very implementable controller, of course, no problem. Yeah, it's just a function of the states. Yeah, no issues. All right, but of course you notice that it contains the parameter, right, which is again something that you expect. Okay, in fact x2 desired also contains the parameter, so the parameter appears here, right? So the parameter is, it's complicated. Yeah, the parameter appears here, the parameter appears here, right, and the parameter also appears here. Yeah, so unlike the matched case where the parameter appeared in only one place, here the parameter seems to appear in a lot of different locations. Yeah, and this is what you will see subsequently complicates the adaptive controller design. Okay, so we'll sort of start going into the adaptive control design for this same system now. So what happens in the unknown parameter case? So of course in the unknown parameter case, as you can see, I cannot have an x2 desired, because I think of x2 as a control, right? So I cannot have x2 desired with the theta, right? Because, well, I don't know theta. So there's no question of implementing a theta. So therefore, the first step is again standard certainty equivalence, right? Because we're just looking at the first system, right? So the first system is x1 dot is x2 plus theta fx1 with this as some what one would call pseudo control. Okay, so x2 desired is with a theta hat, which is basically an estimate of theta with fx1, and then of course you have the nice negative term. So when x2 is in fact x2 desired, you will get x1 dot is minus k1 x1, but and now with an additional theta tilde term, right? So this is unusual. You already start getting a theta tilde here in the first piece itself. Okay, this is where things start getting complicated. And now what do? Earlier we took v1 as 1/2 x1 squared, but now that is not sufficient, right? Because now I have a new state. So what do? I do what I do typically in adaptive control. I add a quadratic term corresponding to the parameter error. Yeah. And now I use that to construct an update law, right? So what do I get? I get here x1 dot and 1 over gamma theta tilde theta hat dot, right? And now I plug in for x1 dot, which is this, and then retain this term as it is. Now I know that this theta tilde terms can be combined nicely, right? And if I choose theta hat dot to be this, yeah, which is essentially cancelling this term out, which is the best I can do. We've already discussed this several times before. Then we are left with v1 dot is minus k1 x1 squared, which is negative semi-definite, right? Right? Again, try to remember the difference from the matched case. In the matched case, when we took the v1 dot in the ideal circumstance, this is the ideal circumstance because x2 is assumed to be exactly x2 desired. So even in the ideal circumstance, V1 dot is coming out to be only negative semi-definite. Whereas in the earlier version, in the matched case, V1 dot came out to be negative definite. Expression was exactly the same, but there was no theta tilde state. Therefore, the V1 dot was coming out to be exactly negative definite in the matched case. So that's what I will actually make a comment on. Negative definite in the matched case. Yeah. So again, things are more complicated in the unmatched case, right? So now what? We of course know that x2 is not identically equal to x2 desired. So we do the best we can. We try to have x2 track x2 desired. And for that, we introduce a quadratic term in the backstepping error. Yeah, so we are trying to drive the backstepping error to 0. So obviously we introduce a quadratic term in the backstepping error in the form of v2, right? And this is again the same, right? And now what we would want to do is, right? So in fact, I would say want to choose. What we would say is we want to choose the x2 dot, which is the control, to be just again the same as before, which is canceling these guys out. Okay, but now remember that x2 desired contains the theta hat, right? Another state, no longer the theta, which is a constant, and the derivative of the constant being 0. Yeah, so when I take the derivative of x2 desired, that is, I compute x2 desired for its implementation, what is it that I will get? I will get this minus k1 x1 dot, which is fine. Yeah, then I get this term is actually, write it down, this term is minus theta hat dot f x1. All right, this term is minus theta hat dot f x1, and if I plug in this theta hat dot here, this is what you get. Okay, this term is just minus theta hat dot times fx1. All right, and then the next term is just, I mean, because we are doing the product rule for the differentiation, right? So you have theta hat dot fx1 and theta hat f dot x1. Okay, and you know what happens is that, I mean, I of course plug in for the x1 dot. I keep the theta hat f dot x1 as it is, right? But notice that theta hat f dot x1 is also theta hat partial with respect to x1 times x1 dot. So not just an x1 dot here, but also an x1 dot from here. Okay, so that's what is written here. So this actually becomes, I mean, we don't need this step. This actually becomes k1 plus theta hat del f del x1 dot. In fact, this is what we had even here in the control law, minus k1 minus theta del f del x1. So this theta gets replaced by theta hat x1 dot. Yeah, so that's the same, right? So that's what you have here. And you have minus gamma x1 f squared x1, which is just coming from this term, the derivative of the estimate. Yeah, great. Now you of course substitute for x1 dot also, because we want to write the whole thing, right? We want to write the whole expression, right? Excellent, excellent. So so what we are sort of trying to understand is that whether the control is implementable or not. All right, and this is where things start to get wiry in this case, in the adaptive case. If you notice, this x2 desired is of course implementable. That's how we chose it, right? I mean, we introduced the theta hat in x2 desired just so that it is implementable. And typically we assume all the states are known and theta is unknown, but then because theta is unknown, we introduce a theta hat here. So therefore x2 desired is implementable, right? So in this control, x2 minus x2 desired is of course implementable, but there is a problem with x2 desired dot. And why is there a problem? Because if you note, when we took the derivative carefully, we came to this step. Everything is implementable, but then we reintroduce the theta. How did we reintroduce the theta, which was an unknown? Because of x1 dot. Okay? Because the derivative of x1 shows up in the control law. Because of this, therefore, we reintroduce the unknown. Okay, so this is where we sort of start to have an issue with the implementation of the controller. So that's what I will say. So in fact, I'm going to highlight this. So due to this, control U is not implementable. All right, the control U is not implementable because of this theta. Okay, so um, that is what we say contains the theta dot, which is unknown. All right, so that's what we want to do. Now we want to figure out what we need to do. Right? We need to figure out what we need to do. We of course do the sort of obvious thing. Yeah, instead of uh, having a theta, we replace it with a new estimate theta mu hat. Okay, so because there is an unknown here, every time we get an unknown, that's what we do in certainty equivalence. We replace it with the estimate. But the problem is, the key problem to remember is that, so replace with estimate is the usual solution. Is the usual solution via the certainty equivalence principle. All right, but we cannot use theta hat since theta hat dot already specified. Yeah, since theta hat dot is already specified. Yeah, because theta hat dot is already specified, when you do the Lyapunov analysis with this theta tilde squared, this guy, yeah, it will only cancel this one term. It will not cancel the theta tilde term that you get because of this change in the control. Yeah, this term will not get cancelled. Okay, and of course you also want this term to be cancelled, because I mean, in the ideal circumstance this term goes away, but in the adaptive circumstance, that's how we cancel this theta tilde terms, or the parameter error terms, is by introducing a Lyapunov function and using the update law for the theta hat dot in order to cancel this term. Now if we are unable to cancel the term corresponding to this, we'll be left with a non-negative definite term in the Lyapunov function derivative, and that's a problem. And therefore, we need to introduce a new estimate, mu hat. Yeah. So for the same quantity, we have a new estimate, and that's what we do. So this mu hat is what replaces theta, and we of course construct an appropriate Lyapunov function, and we will look at the Lyapunov function construction and the subsequent analysis in the upcoming session. All right, great. So what is it that we looked at today? We sort of are continuing our analysis of this unmatched case, which, as we can see, is turning out to be much more involved than the matched case. We saw what the differences are. We saw that the x2 desired starts to contain the unknown parameter. Yeah, and as we go into the adaptive case, where of course theta is assumed to be unknown, we land in some trouble in terms of how to define the update loss, and then in the end we come to a situation where the control which has this x2 desired dot, also contains the theta again. So the theta seems to reappear, and then we are looking for a way to deal with this. So we introduce a new estimate for this theta into the analysis. So essentially, the only way we are able to resolve this issue at this stage is by having two estimates for the same unknown parameter theta. Okay, so this is very standard in adaptive control, by the way. In a lot of scenarios, we do what is called as over parametrization. All right, so we will talk about this and how this unmatched state backstepping adaptive control will happen in the subsequent sessions. All right. Okay. See you folks again. Thank you.